In this module, I will discuss options environmental engineers have to remediate groundwater pollution. The first is hydraulic control of plume movement. This is considered removal or control, but not remediation. What is performed is a central well is drilled, and pumping or overpumping creates a cone of depression in the subsurface. And so as the contaminant plume moves this way, cones of depression or wells are created such that the contamination is pumped out. And anything outside of that cone of depression or that capture zone would continue to move around the well. So remember, if you have a well and you have a water table, around that well there is a cone of depression that's created. And this is the capture zone for the contaminant plume. In order to design a capture or hydraulic control, you must have a very good understanding of groundwater hydraulics. And so groundwater or hydrogeology modeling is really critical for this. The second option is an extension of the first. In the first, we simply controlled the movement of contamination by pumping it. In the second option, we would then treat the pumped water. So the contaminated groundwater is pumped out of the ground and an ex situ treatment is designed. The other option, if you don't treat the water, is to recharge it in deep subsurface where it would not pose a public health risk. This is not as desired as actual remediation and treatment. One of your learning objectives is to discuss the difference between removal and remediation. And remediation is the actual breaking down of the compound. In order for hydraulic containment or pump and treat to be effective, we must remove the original source of the pollution. You can imagine if you have a landfill here that continues to seep leachate into the subsurface. Instead of treating here with a pump and treat forever, we first want to remove the leachate, the source of the pollution, and then we just have to pump and treat the residual. For example, leaking oil drums or tanks must be removed, and the surrounding polluted soil must be cleaned up. This is a picture from a web page of a pump and treat system. And I've asked you to also read a Lawrence Journal World article about a pump and treat system in Lawrence. So here you have a plume that's being hydraulically contained because it's being pumped into the well. And then as the pumped water comes up, it goes to a treatment facility in a building, and discharged water can either be discharged by surface or pumped back into the ground. If the contamination source is not removed, then pump and treat is very expensive and is very inefficient because it has to be performed as long as the original source is present and the time it takes for the hydraulic conductivity to reach your well. The other drawback of pump and treat is it's incredibly difficult to pump out contaminated water at great depths and at unknown sites where we don't understand the subsurface transport. A final drawback of this is entrapped contaminants between soil particles are never removed. And these entrapped contaminants can disperse low levels of contamination for a long time. Pump and treat was very common 20 to 30 years ago, but as technology and understanding of remediation and the cost for pump and treat have been appreciated, these are less favored today. Pump and treat systems that were designed 20 or 30 years ago are still in operation, and so those sites have an annual operational cost to the industries that originally polluted. A third option we'll discuss is the design and implementation of slurry trenches or barrier walls. They are also called groundwater dams. This method involves excavation and the placement of a trench that's backfilled with reactive material. The reactive material is going to be defined by the contaminant because it's designed to interact and remove the contaminant. So the properties of the contaminant will dictate the properties of the reactive material. But some common materials are iron filings, activated carbon, or peat, and these adsorb and transform the contaminant as the aquifer passes through the barrier. Because excavation is required, these are usually designed for shallow aquifers. A picture of one of these is here. You have your plume that's moving. It's fairly shallow. You would excavate out an area of the soil that will intersect the plume. As the contamination passes through the reactive media, clean water would come through, or remediated groundwater. Some of the drawbacks of this are the cost and time needed to construct the barrier. Once the barrier is completely spent or all of the active sites are covered, it's almost impossible to regenerate that material in situ, meaning in the soil. And so you would have to excavate the reactive media and replace it. For this reason, researchers such as myself have investigated biological barriers where you can have microorganisms that degrade the contaminant as it passes through. This leads us to the next option, which is in situ biological treatment. In biological treatment, we use microorganisms to break down the contaminants into smaller compounds, and ideally non-toxic. But there are problems associated with this, which I'll discuss. The microbial organisms utilize the contaminant as food, and through metabolic or enzymatic processes, which you can consider eating, they break that down into smaller compounds. Biodegradation is a key process to natural attenuation of contaminants. And so we'll discuss this as the last option, but some extent of biodegradation may happen without an engineer even encouraging the process. In order to understand bioremediation, it's important to think of the different scales involved. For pump and treat, you have the macro scale. So you have us drilling holes and pumping in fluids, which is going to include nutrients to encourage microbial growth, and then recovery of some materials, ideally broken down or derivative compounds. Then you have the mesoscale, which is when the oxygen and nutrients are transported through the soil particles. But the microorganisms, they live and work at the microscale because they are microscopic. They range about 1 micron in diameter. And so the efficiency of this is really dictated by the microscale interactions of microorganisms, the contaminant, and water. When bioremediation is performed at a large scale, we typically will pump in nutrients or oxygen into the subsurface to encourage microbial growth. Now, as one of your learning objectives, I've asked you to memorize this pathway, and I'll cover it in class again. This is a classic pathway for perchloroethylene mineralization. And mineralization is a vocabulary word that means the contaminant goes all the way to carbon dioxide. Complete mineralization. The reason why this pathway is important to note is you start with perchloroethylene, which is carbon double bonded with 4 chlorine atoms attached. And each of these steps is performed by a microorganism. For each step, you'll see that one of the chlorine atoms is knocked off. So here you end with trichloroethylene, and then any one of these can be knocked off again. So here we have dichloroethylene, and it doesn't matter which of these are knocked off. And then you knock off a third chlorine, and you end up with something called vinyl chloride. And the reason this is significant is vinyl chloride is much more toxic than the original parent compound, PCE. And so this is a great example of how biological products can be worse than the parent compound. And yet, we would still try to encourage biodegradation because this is the only way to get to carbon dioxide or complete remediation. So it's also a great example of the old adage, it gets worse before it gets better. So bioremediation is an interesting technology because it does have the potential to completely mineralize and remediate pollution, and yet it is not without its challenges and difficulties. The next option engineers may utilize is vapor extraction. And this is an example also used from the Lawrence Journal World article. This is typically used for contaminants that are volatile. So for instance, gasoline is a compound that may be able to utilize this. It's also encouraged for compounds that are present in shallow aquifers. And so in this example, you have the contaminated upper aquifer, and you would simply take fresh air, you would blow it into the aquifer and sparge air into that contaminated layer. It would volatilize the volatile contaminants such as gasoline, and you would drill relief wells. And all of that vapor would go into a vapor extraction building, which typically utilizes activated carbon to absorb that vaporized chemical, and then you would vent treated vapor to the atmosphere. This can be an extremely effective procedure for volatile contaminants, and also a very small footprint. Some of the limitations for this is that you need a fairly high permeable zone for that gas sparging to work, so low permeability zones are difficult. It's difficult to get good extraction at depth, and it really is meant to extract volatile fractions, so multi-component phases such as liquid phases with a low volatility are not appropriate. The next treatment option we have is excavation, followed by landfilling or incineration. This is typically done to some extent at old gas stations around the underground storage tank, and it's often done in conjunction with other technologies. So removing the source is typically excavation, and then you may apply pump and treat or bioremediation or vapor extraction for the plume that has moved away. It is very expensive for large or urban sites because it is hard to excavate those sites. It's expensive. The last technology I'll define for you is natural attenuation. And this is one we will talk about in depth in class for the Norman, Oklahoma. But natural attenuation refers to essentially doing nothing from an engineering approach except for monitoring. It is letting natural processes work and monitoring those to make sure that there's no imminent public health risk. Because it is only monitoring, it is a very practical and cheap engineering strategy, and it is also appropriate if there's no public health risk. Natural processes can be complicated. They can include all of the ones that we just spoke of, but on a smaller or a slower time scale. It can include bioremediation, volatilization, sorption, and dilution, but it usually takes time to perform. And we'll see this again in class.